Hi, I'm Neil Krawitz, and this is the talk on image analysis and forensics, a picture's worth. In this talk, I'm going to give you a little bit of background about the problem space of image analysis. And then I'm going to cover a lot of different analysis methods. And finally, I'll go into a case study that I call Dr. Z. So about the problem space. Pictures have power. They may be traumatic, empowering, or just painfully funny. But powerful images influence society. With the advent of sophisticated digital imaging software and photorealistic graphics, artists are allowed to strengthen their images or convey alternate meanings. Unfortunately, many of these altered pictures are presented as if they were real. They may be modified in order to convey a point or to influence opinions. They also may be designed to demonstrate a specific technique or some information. There's, of course, implications in a lot of different fields. For example, in the mass media, a mislabeled headline may make people angry, supportive, anything like that. In legal circles, there's a lot of issues here. Take child pornography as an example. Pornography by itself is protected free speech. Hustler, Penthouse, Playboy. Ooh, a lot of feedback. On the other hand, child pornography is illegal. However, in a 2002 ruling by the Supreme Court, virtual child pornography, where no real child was ever used in the picture, is considered pornography and not child pornography, and therefore it's protected free speech. If you're law enforcement and you have a hard drive from a pedophile with all these pictures of kids on it, it is up to you to determine whether the pictures are real or virtual. And if they're virtual, then you can't prosecute based on them. And then there's a third problem with images being used as security for like authentication. Take Yahoo as an example. If someone has taken over your Yahoo account or is impersonating you, you need some way to authenticate yourself. What Yahoo wants you to do is send a copy of your photo ID. Now, there's nothing to say that the person sending in the photo ID is the person on the photo ID. They just happen to have a copy of it. But they want you to send that in. Not only that, but they want you to fax it to them. Fax is really low quality. Any doctored photo should be able to make it through. As another example, there's MySpace. If someone's impersonating you on MySpace, they want you to, and I'm not making this up, they want you to send in a picture of yourself holding a sign that says MySpace and your MySpace ID number on it. If this sounds familiar, it's probably because you've been to 419eater.com, where they make fun of people who run Nigerian scams. So let's see, we can go on to Google and search images for man holding sign and pull up a picture like this. And then using Photoshop, we can erase the board. And then we can write in our own MySpace identification number on it. And I will tell you that I have firsthand knowledge that this type of forgery is acceptable by MySpace. Now, I know what you're thinking. Jeff Moss runs BlackHat, and wouldn't it be nice to disable his MySpace account? Unfortunately, this guy doesn't look like Jeff Moss. Not a problem. There's a couple of different ways to fake photos. You can do the old school method, which is to do like staged or mislabeled images. And those are not detectable with the approaches that I'm going to show you guys. The reason is the picture is still a real picture. It's just the content is misrepresented. Then there's old technology like negative splicing and airbrushing, which may be detectable with some of these methods. And finally, there's the high-tech approaches. Things like digitally spliced or digitally enhanced images, pictures that have been shopped, Photoshop, GIMP, anything like that to modify the picture. And those can be detected. To give you a couple examples of old school fakes, this first one is from was taken in 1914, and it's from the Belgian War. Apparently the reporter thought it would be really funny to pose with some soldiers. He never expected the newspaper to actually run the picture as if it were real, or to make up a story to go along with it. More recently, we have people like Adnan Hodge, who used to work for Reuters. He would take pictures of things and submit them, and a lot of times the pictures were doctored or staged. Here are two pictures taken reportedly weeks apart, yet they show the exact same woman wearing the exact same clothing. We get into bigger problems when you start mixing old technology and new technology. For example, take photos that are real, something like a 2002 dust storm in Australia. Someone digitally enhanced the picture by removing the timestamp in the bottom corner and then claimed that it was a 2004 tsunami hitting Sumatra. I can't tell you how to tell a tsunami from a dust storm, but I can tell you how to detect that the timestamp was removed. So the big question becomes, how do you distinguish real pictures from computer graphics? How do you detect image manipulations? And how do you pull out information from images? For example, if it's a real picture, can you tell who created it, where it was created, when it was created, how, anything like that? If it's digitally enhanced, what was enhanced and how was it done? And same thing for computer graphics. To answer these questions, we use a large number of image analysis techniques, and I'm going to go through each one of these. Starting with observation. This is a picture that's been recently circulating a lot of IRC channels this is a picture that's been circulating a lot of IRC channels and claims to be a wares factory. A wares factory is a place where someone mass produces unauthorized copies of software. And we can see the duplication machines. We can see the ink pad in the bottom corner for attaching the official seal. And we can see the printers on the side for creating the CD covers. So the question is, if this is currently circulating IRC channels and wares channels, who created this picture? When was it created? Where? Anything like that? To answer those questions, we just need to take a look around the room. For example, there's a poster. The poster has Spanish text on it. So the country is probably a Spanish-speaking country. Mexico, Venezuela, Argentina, could be anywhere in the world. The poster itself is for the movie Tarzan and Jane, and says that it's coming out to DVD and video on March 26th, but they don't give the year. Fortunately, we can go to the Internet Movie Database and look it up and find out that this movie was released in most Spanish-speaking countries on March 26, 2003. Since movie posters usually are not released more than a month or two before the video comes out, and they're hard to find items a month or two after the video comes out, this gives us a time frame, somewhere between January and May 2003. The other movie poster back there is Harry Potter and the Chamber of Secrets, which was released in most Spanish-speaking countries on November 2002. The other thing we can do is look at something in the front corner. There's this bottle down here, and I've actually scaled it up and sharpened it, and, well, on my screen you can actually read it. It says at the top, alcoholo de 96% sanitario. This is isopropyl alcohol. I showed this picture to Pedro Bueno from the Internet Storm Center, and he noticed that right above the circle B is the word Madrileno, Madrid. This isn't any kind of Spanish. This is Spain Spanish. Now we have a time and a location. The main things to look for in pictures are things that will give you a sense of time or location. Clocks, calendars, dated material. For location, look for things that are language-specific or region-specific technologies. A lot of times there's pictures of currency. If you can identify the currency, you can identify the country. Same thing goes with electrical outlets. They differ by region. The other thing to ask yourself is, what other information can you pull out? For example, on the computer screens here, I cannot tell you what the application is. I don't know what the program is, but I can tell you that the operating system is Windows. And since it has a solid color title bar going across the application, it's probably Windows 95, 98, NT. It's not XP or ME, because those have this gradient by default. Now, this type of observation can actually be done on computer-generated images, like this picture of an astronaut created by an Italian artist. This actually won the Computer Graphics Choice Award from the CG Society in 2006. According to the artist, this picture is based on a NASA photo. And here's the actual NASA photo, so we can compare them side by side. And the artist did a pretty good job on it. I mean, I can understand why he would remove the dust from the spacesuit, but there's a couple of things that stand out as being different. For example, the original spacesuit looks wrinkled, while the artist's rendition looks puffed out. And if we take a closer look at things, like on the torso, we can see that on the torso box, of the original spacesuit, there's a dark grounding screw, whereas in the artist's rendition, there's a light-colored grounding screw. The artist also put 6 very shiny screws around the red and blue torso connectors. Those aren't visible in the real spacesuit, but they do exist. However, they're not shiny. They're actually non-reflective. The artist also included a metal clip on the belt. Now, as it turns out, the artist created this image in 2006. In 2005, IMAX created a movie called Magnificent Desolation, in which they recreated the famous moonwalk. And if we take a look at a behind-the-scenes picture of this astronaut, we can see that he looks puffed out, not wrinkled. The middle torso grounding screw is light-colored, not dark. There are 6 very reflective screws around the torso connectors, and the belt has a metal clip. Even though the artist likely based his position of the model after the NASA photo, he likely modeled the spacesuit after the IMAX movie. So that's enough that you can pull out of observation. Let's go into format analysis. Formats are information. It's data holding data. So when you make a change to a picture, you're going to modify the format itself. I'm going to use JPEG as just an example, but a lot of these analysis techniques work with GIF, TIFF, PNG, and pretty much any other format that you can think of. JPEG has a set of key features, things like metadata. Almost every JPEG contains metadata about the picture. There's a quantization matrix for lossy compression. There's the lossy data itself. And there's how it processes the image in these 8x8 pixel squares. When you see a JPEG that's really sort of crappy looking with all these blocks on it, you're actually seeing JPEG artifacts, which are the 8x8 squares. You're actually seeing those squares. So the whole thing is, if you can identify the feature and identify an inconsistency within the feature, then you can identify the manipulation. For example, if you take a picture with a digital camera, you usually store in it, or your camera usually stores in it, meta information about the type of camera that was used, the make, model, version number, how far away was the subject, was the flash used, what was the aperture, all of this information. It also stores things like the date and time. A lot of JPEGs from cameras also store multiple pictures in them. There's the big picture that you see when you transfer it to your computer, but there's a smaller picture that's actually the same size as the view screen on the back of your digital camera. This way they don't have to shrink it down when they're rendering it when you say preview. If you have a couple of different digital cameras, you can usually map the size of the small image to the correct digital camera. However, there are some problems with this metadata. For example, it can be modified. That's uncommon, but it can be done. It can also be inaccurate. How many people brought a digital camera with them? Yeah, how many of you set the time zone when you arrived? Yeah, the time is usually wrong. Another big problem that comes out of the metadata comes from applications that don't update the information. For example, I can take a picture from my digital camera, bring it up under Photoshop, draw on it, manipulate it, move things around, paste things in, and save it. And when I save it, Photoshop will keep the camera meta information even though it's no longer accurate, and it won't tell me what modifications were made. So the question becomes, how do you tell if the metadata is accurate? And we do that through quantization table fingerprinting. You see, these quantization tables, which are used for image compression, should be computed every single time you save the image. However, that's CPU intensive, and most cameras don't have that kind of horsepower. And it can also slow the user experience. Imagine saying file, save as JPEG, and having to wait 20 seconds while it computes the tables. So instead, most applications in digital cameras have these tables hard-coded. If your camera has